the thing. Good. So now we are recording the lesson as I am required to do. So I was saying that I myself, I'm a chemist. My major was in physical chemistry. And in this lesson, the idea is that we try to see a bit how biogeochemical cycles work, not just in the atmosphere, but through the different component of Earth system, like ocean, land, and so on. And we will try to see how you can model these processes. Of course, I'm not expecting that you became a proficient ecosystem model, but the idea is that you should learn enough to be able to understand how an ecosystem model works and possibly learn how to critically interpret the result of this ecosystem model. So before we move on, now we are 3, 6, 9, 10 plus, I guess, some from the technical stuff. Good. The idea is that maybe you can say something about you, so that I know who I'm talking to. So we may start with Coyote. Do we have a coyote? How do you say that? So where are you from? Tell me something.
Okay, hello, sir. My name is Kayode Ayibusi from Nigeria
Really?
with a meteorology background.
Meteorology.
Yes.
Uh-huh. Okay, and how come you're here?
Sir?
Yeah, what do you expect from this course?
Okay. Uh, I expect to become better in its atmospheric chemistry and biogeochemical cycle. So I expect to understand the cycles that happens in the atmosphere and the models. So at the end
Good.
of the course,
Very good. So who is next? Let's say Alejandra Quintanilla. Huh? Right? Easier for me this.
Yeah. Well, I'm from Mexico and I study geophysical engineer and I do the master in physical oceanography.
Good. And then let's move. We have Mickey. Michi De Vera.
Yes, hi sir. I'm Michi De Vera.
Yeah, Michi.
So I'm from the Philippines and I just finished my bachelor's degree in applied physics and material science engineering.
Good. And the next in line we have Aminata. Aminata. That's you.
Hi,
Hi.
I'm Aminat Ambelaro. I'm from Nigeria and I have a bachelor's degree in physics. Yeah,
Okay.
thank you.
So Nigeria, Mexico, and Philippines, and all of you are physicists. So and then we got Tawfiq. Huh? Tawfiq. Oh, how do you say that? Huh? Yeah, Yakubu. This is you. You have to unmute your phone, otherwise there is no possibility for me to listen to you. You have to unmute your phone.
Yeah, good afternoon.
Good afternoon.
Yeah, I'm Tofik Yakubu. I'm from Ghana and I completed my BSc in 2019 in physics with geophysics.
Okay. From Ghana.
Thank you. Yes, from Ghana.
Okay. So Ghana. Okay. I have a map there.
Yeah,
Photo
West
request.
Africa.
You persona don't always have a clear idea of the rest of the world.
Yeah, that's nice.
And then we get Grace. Who is Grace? You.
Hi, I'm Grace, and I am from Ghana as well. I studied meteorology and climate science.
Mhm.
Yeah.
So again, climate science. Then we get Amalia Sanchez.
Hello,
Hello.
my name is Amelia. I'm from Cuba and I have a bachelor degree in physics.
Okay. Then we get. Oh, that's impossible for me. That's Vu. Where are you from?
Okay, hello, so I'm from Vietnam. My name is Dung. I'm just has finished mechanic mathematics.
Okay. So
Okay.
you have something different. And the last one is Bel Bashir.
Yeah. Hello, everybody. So my name is Belbashir Tariq. I'm from Algeria, and yeah, and I have a master's degree on geophysics.
Good. So that's complete, I believe, our self-introduction. And we can start to move on. Let me check. Because, you have this remote session, it's always a bit complex. So I'll try to, let's see if this works. So condivido schermo. Okay. I'm trying to share my iPad so that
Yeah, hello.
yeah, good. We cannot.
So I don't know. Yes, it's interrupting when you are talking. So I don't know if it's only me experiencing that or the others too are experiencing that.
But in principle, you should be able to see my screen, eh?
Yes, I see
Yes,
it.
yeah, I see your screen, but there's a sound at the background, when, and I don't know if the others are experiencing it too.
Yeah, the sound is not good.
Yeah,
Yeah,
it's not
I
good.
think that the person that is not talking have to mute his microphone because I think that's the sound.
Oh, okay, then Tariq and I, you have.
Well, that's much better, isn't it? Good. So it was Tofik, it was you. Hmm? Good. So somehow let's try to keep this as interactive as we can. So I got a screen there so that I possibility to write and this is not on studio and possibly pointer. Okay, we will see. And I also have the possibility to see your faces. So if you want to say something, please do that. And we can talk and we can try to make the most out of these lessons. And usually I go on pretty slowly because I have been told that these topics are relatively new to most of you. But if I'm going too slowly, you just tell me that so that we can speed up, and that's not a problem. So again, my name. This is my email where you can find me. This telephone number, I'm not sure that you can get me here. Anyway, I have two offices. One of the offices here in the campus, and you can reach me at this email anytime. And I will provide to you somehow, maybe we can share a folder or something, or the PDF has some additional material. And so that you have the possibility to go over the notes whenever you want. My suggestion is that you but then this may not be the case. Lesson, because I am told that we will have the sustainability earth system, and we will go through the chemical composition of seawater, ocean, and distribution of salinity, and then we will see how the other compounds are distributed around the planet. Here we start to put some attention to life, which is totally different from the non-living matter. Just to mention something, these systems are totally far from thermodynamic equilibrium system. So here the thermodynamic laws are somehow different. And then something on models. I have been told that because of the COVID, we have just 5 lessons. In the past, we got the possibility to get maybe 5, 6 lessons just to revise a bit the chemical principle and thermodynamical principle, and then we used to get through this stuff. But in this situation, it seems that this is not possible. So we will squeeze a bit the material, and I will assume that you are already familiar with chemical principle, like what is kinetics, what is an equilibrium constant, what are thermodynamical potential, and so on and so forth. Are you? Is my assumption correct? You can move your head and you can say no, maybe something, well, something. So if I say what's the difference between entropy, enthalpy, and free energy, is this clear to you or maybe not so clear? Not so clear. So good. It's better to know that so that when we go there, if this is needed, we can spend a few words or possibly I can try to write you something. Okay, move on. Earth. Earth is a very special planet. So far, if you go through the Grand Star catalog, there are billions of bodies in the universe. However, as far as we know, we have just one planet in which we have life. And so this is a very peculiar planet, and it may be worth to have a look at how it is structured. What is the atmosphere, the hydrosphere, the lithosphere, the biosphere? You know, we get a number of spheres, but if you cut down the Earth, like maybe you already seen this picture, you get that maybe 6,000 kilometers. And what is of interest to humans is just this very tiny crust where we live. However, Here we have a zoom. This is the soil. Actually, just the upper part of land is soil, it's not land. And the soil has peculiar properties, no? You get worms, you get unique substances, you get something that make this land fertile. You can grow stuff here, like vegetables. And you can get living organisms habitat this very, very thin layer. Now, the biosphere is something that is not easily put in a geographical context, meaning that biosphere, well, living organisms have their put on the foot on the land, they breathe in the atmosphere, but we may say that roughly there is no life in the atmosphere, but for few birds, but the birds are very close to the land. And we may say that most of the life is in the lithosphere, so the part of solid earth, but not interior, not the mantle, just the surface. Okay, and here we get ocean and land. And so biosphere go across the hydrosphere, go across the lithosphere, and for a small fraction on the atmosphere. So let's make a step back, and this is the planet as you may be able to see it from far away, and we see that it's mostly covered by water, ocean, and what do we see also? It is a closed system. So closed mean what? Mean that from a thermodynamic point of view, you may get open, closed, and isolated system, right? So open, your body exchange matter and also energy. This is not the case. Isolated means that the body does not exchange anything. This is not the case either. The Earth planet is a closed system because it exchanges energy, it receives energy from the sun and it radiates energy towards the universe. So there is some exchange of energy, but there are no input or output of matter, but from some meteoric minor stuff. So it is a closed system. And then matter is constant in the universe, in the planet, and this process, you get transformation of matter from one kind to another kind, and you get recycling. Yeah, we get a missing N, as you will see. I have many typos in my note. So matter is recycled, energy, of course, is conserved, meaning that you get a flow of energy on your planet and the equal flow of energy out of the planet. And energy is conserved, matter is recycled. What is driving all this transformation is the entropy increase. So what is entropy? We may talk for hours about entropy, but in this context, we say what? Not all the energy forms are born equals. You have some possibility to get work from some energy form, and you have a different possibility to get extract work from a different energy form. Some energy form are more useful, if you want, than others. And short-term radiation, light coming from the sun, is a pretty noble, pretty good energy form. With while the heat, which is irradiated back from the Earth, long wave radiation, infrared, is a poorer energy form, okay? Because you get less possibility to extract energy from that. What do you use to measure the energy quality is entropy. So you get a given amount of energy coming from the sun. This is a very low entropy. And then the same amount of energy degraded somehow, much richer in entropy, that go out into the space. And this entropy production is the driving force that run the dissipative structure and keep them far from the thermodynamical equilibrium. Okay, let's say it in this way. This was not topic of the lesson, but since we were here, let's start to talk about that. CO2 carbonic dioxide in the atmosphere. So you get a carbon, and let me see, you get a carbon, and you get oxygen, okay? And here you get a double bounce, and this is a pretty strong, bond. Then through photosynthesis, you change this, it became something like this, sugar and organic matter, leaves, organic being. You yourself are made by this carbohydrate for most of your material. This is something like this. Oh, let me see if I remember properly. Something like this. No, something like this. COH. And this is a much weaker ligand. The bonds between the atoms are much weaker. Or maybe you get something like this. And these bonds are much weaker. Since in the atmosphere you get a lot of oxygen, you may expect that this oxygen, which is very reactive, is a strong reagent, would react with this and produce, in this case, CO2, NO, and water. Because this kind of reaction is favored from a thermodynamical perspective. And indeed, this is what happens when you die. When you die, your flesh is decomposed with reaction like this one. But while you are alive, there is something that keeps you and your body out far from equilibrium, keep you in the less stable situation. But in order to stay there in the absolute level of the energetic level, you have to keep on fighting this degradation process. And you use energy, actually you use entropy, and this makes you a dissipative system. In order to stay there out of equilibrium, you need to continuously process the energy incoming and changing the entropy density of this energy and use the difference of entropy from the incoming and the outgoing energy flow in order to keep you out of thermodynamical equilibrium. Okay? So, the planet, this is always true. The planet is closer, matter is recycled, energy is conserved, and the entropy increases. And life develops everywhere, driven by this entropy increase. On the right side of my slide, you get a picture that reminds us of the so-called United Nations Development Goals. They are pretty popular these days. And maybe you didn't know that, but the United Nations every 10 years devote a decade in tribute to something. So the current decade, 2020-2030, is named after decade of ocean science for sustainable development, and this is very important, in my opinion. First of all, because it's devoted to science, so it's ocean science, but it's science. Then it's ocean. This recognize the fact that we know very little about the ocean, and we have to be extra careful in ocean exploitation, because we do not want to make on land, on ocean, the same mistake that we already made on land. And we want a sustainable exploitation of the ocean. Here you also get the different goals. This is a picture in Italian, and you may not, even if it were in English, you may not be able to read it, but you can get this kind of picture anywhere in the web. So first goal, 2030, in 10 years, is fight hunger and poverty. I think this is fight poverty. We do not want poor people in the world any longer. Very nice. We do not want to have people that have no food, even better. And then you get education, gender balance, and you get many different things. Climate, proper climate, and you also get life underwater, and then life on the land. So these are very broad, very general goals that United Nations, the world, set as proper goal for humanity in the next 15 years or so. However, even if all those goals are very important goals, the picture here reminds us that there is a hierarchy in this goal, meaning that you have no possibility to, let's say, fight the hunger, provide food to everyone, if you destroy the biosphere. So at the very bottom, at the base of everything else, you get a few goals that are related to the need to preserve the planet and the planet capability to provide food and provision and ecosystem services. We use the word ecosystem services for nature contribution to humanity. This may be food, but this may also be the oxygen that the plants produce for us, maybe pollination, maybe many different things, and maybe we will have the possibility to talk about this again. And if your biosphere is preserved, the next level is to get a proper society, equity. We do not want people fighting for food, fighting for land. Otherwise, there is no possibility to maintain the current state very long, because we will have fighting, we will have war, we will have something that will change the reality. And only if you get proper biosphere and proper society, at that point you may focus on the economical component and say that you also want the smart society, meaning that you may want increasing the richness of all the planet. Fine, but this is possible in a sustainable way if and only if there also is a social equity and a very low impact on the biosphere. Otherwise, this cannot last. So, it may seem a bit far from our talking, but in a way it is not, because the point that we want to stress is that the planet is just a planet, and everything is deeply interconnected, maybe on different time scale, but you have to be aware of the fact that when you change something in a place of the planet, this may have an impact on something else in a different part of the planet. And nowadays, we do have the possibility to make an impact in the planet. So I said before that Earth is a very special planet, and maybe cannot remember when. Let's say 30 years ago, there was a guy, Sir James Lovelock, that developed a very controversial book. The book was called Gaia, and the guy was Jim Lovelock. And Gaia became a very popular concept. And I'm pretty sure that most of you heard something about Gaia. Gaia was popularized as the idea that the planet itself is a sort of superorganism, like a living planet. And we got science fiction books, movie about that. And this was not, by the way, what Sir Lovelock meant when he wrote this book. Still, there is something on that. And one of the idea is that if you get a planet like Earth in the same position, same distance from the sun, same dimension, this would be the equilibrium composition of the atmosphere. Most of the atmosphere would be carbon dioxide, there would be no oxygen, and the rest. While in the present world, we are here. So there is a very large difference between the equilibrium world and the present world. And the difference was so large that this Lovelock said, clearly there are some feedback, there are some mechanism within the ecosystem functioning at the planetary scale that keep the planet far from equilibrium condition. So the difference between the present world and the equilibrium world is life. And life do something that keeps the condition which are useful to life. So we get positive feedback that keep the system as we wish it. And this is why someone say this is a superorganism that works as to keep the condition that the superorganisms want. Other say nonsense. We just get a number of positive feedback that make a more stable and stronger one of the many possible equilibrium. Anyway, the concept stress the fact that we do have a number of connections between the different Earth system components. By the way, and this is a parenthesis that does not pertain to the course, Sir Lovelock recently wrote a new book. Now he's 19 years old, but he brought this Nova Scene. It's a short book, and you can get it from the ICTP library, in which he said that we no longer are in the Anthropocene era, we are in the Novacene era, and the Novacene era in the Lovelock view is like Matrix, you know the movie. It's an era, a geological era, in which we have the machine, the robot, the artificial intelligence that take the lead and will somehow replace the humans and humanity. And in agreement to Lovelock view, we are already entered into this new era. But this is just a curiosity. So let's make another step. We have been talking about the planet, and this is a recent concept. I mean, 2 centuries ago, there was no possibility for the humans to make anything able to really change the planet. But now, after the Industrial Revolution, we got modern technology, and this really gave us the capability to modify the planet to an extent that we never saw, so that we also got the feeling that we human beings are not part of the ecosystem, are not part of the planet. We forget that we are animals, and we think that we can impose our own rhythms, tempos, historical times, time scale to the nature. So for maybe 5,000 years, humans live following an agreement with a biological time scale. Now we are living in agreement with a historical time scale, and we impose this time scale to the nature. And we think that we can manage everything. But mind you, this is not so. This is not so. And nature very often reminds us that no matter our ambitious, we do not have the possibility to control everything and to fix everything. We are not gods. We are part of the ecosystem, and we have to comply with the natural laws. And this is the core of sustainability, the UN goals that we just saw before, and it's also one of the major challenges that Earth system scientists have to face, because we are not looking at very tiny specific aspect. We are looking at the planet, and we are facing very big challenges. So I'm 100% sure that you already saw this stuff. So this is ozone concentration, very popular a few years ago. So there was, ozone is all over the earth. Somehow it's a shield from sun. And there was very, very, very large changes. And then we get greenhouse gases, like CO2. And you see, this is, what is this? This is, 200,000 years before now. And this is the standard variability. And then here in the last 50 years, we go there. The same for CO2, the same for NO2, and this is what? This is the Industrial Revolution. I mean, this is pretty clear. But it's also pretty clear that regardless the cause, this put the planet in a place that the planet never seen in the last, I don't know how many thousand years. And what? As a biogeochemist, you want to put your understanding on a very long scale perspective. You will see that often we use a box model and a steady state assumption. However, very often is the case in which we have a steady situation, and it's much more frequent that we get oscillation. And luckily, we get some possibility to get records as long as a billion year, like in this case, it was an ice core, you drill the core, you get it, you slice it in very thin plate, and then from whatever you get into the plate, maybe very tiny air bubble, you make some chemical analysis and you get the composition of the gas bubble within the ice as a proxy for temperature in the area in which the air bubble was captured into the ice. And in this way, you get the possibility to say that in the last 800 years, temperature was like that. And CO2 was like this. And you see that there are this oscillation, and you can make some inference about that. Okay. And then you also face other global challenge. We do not have just climate change, we get pollution. Nowadays, everyone talk about plastic, but plastic is not the only pollution that humanity is going to face. We also get drugs. So if you take some water from the Po River here, any major river in Europe, and you run a chemical analysis, you will see that you have an important amount of antibiotics, estrogens, hormones, medicine and drugs of every kind. And no one has a clear idea of the impact of this stuff on fishes and on humans eating those fishes. And no one has a good idea of the cumulative impact of different pollutants that act together. So this also is a serious challenge. And then biodiversity loss. So biodiversity is is a not properly well-defined concept. But let's say that you may measure it as the number of species per square meter. So you go in a forest, you take a box of maybe 100 meter by 100 meter, and with a team of biologists, you recognize all the animals and you count how many different animal species or plant species you get. And that more or less is biodiversity. There are several different definitions. One refer to the Shannon entropy concept. You get n logarithm n, where n is the number of species. But anyway, this is something that is related to the number of different species. And in this plot that I'm projecting for you, you see that in some area, the blue, you still have good biodiversity. But in other area, you get a loss of biodiversity as large as 30%. So we are losing a large number of species. And of course, when they are extinct or extirpated, you have no possibility to get them back. Do we care? We do. We do because all of these organisms not only provide something to humanity, but also plays a very significant role in the ecosystem functioning, in the processing of matter and energy at the planetary scale. Few more slides, generic, let's say, to frame the topic, and then we will go, if we can, what time is it, to more hard science stuff, over exploitation. So how many know what this ecological footprint is? Raise your hand if you know what ecological footprint is. No one? Good. Energy, embedded energy? No, again. Good. So let's say that you want to compute how much natural capital and anthropogenic capital are embedded into something. So let me see if I can find an example. You can do this with everything, but let's say that you get a tree. So you get a tree, and you cut it, and you get wood, and then you transform that, and you get a table. Okay. And then you may want to ask, what is the, let's say with energy, the energy which is embedded energy within the table. And you may say, well, at the very beginning, in order to grow this high, the tree took maybe some, I don't know, 2000 kilojoule of solar energy. And this energy from the sun that the tree uses to grow. But when you think a bit harder to that, you also say that it took some rain also for the tree to grow. And in order to get the rain, you need to get clouds. And so all of these clouds and rain and meteorological cycles was fueled again by solar energy. Because at the end of the day, everything is run by solar energy, right? And so you try to make a computation of how much solar energy is stored within your tree. And you take the share from photosynthesis, you take the share from clouds, and everything else you can think of. But then some man was there and used some saw in order to cut the tree. And this also took some energy. And then they put it on some cars in order to take it to the factory, and they use some gasoline, and that was other energy, and so on and so forth. So now if you get the sum of all the different energy forms, and you convert the different energy forms in the same currency, and this currency is equivalent solar energy, equivalent solar energy, you get every energy form, you transform it in equivalent solar energy, you can make a sum, and you say, well, in order to build this table, we got this total amount of equivalent solar energy, and maybe 30% of it came from anthropogenic sources, and 70% came from natural sources, the sun. Good. If you do this, you compute the energy, EM balance of an object. You can do exactly the same stuff using as currency. Instead of the equivalent solar energy, you can use land, surface of land. Because you can use the surface of land to grow food, to make cultivation, to whatever. And it's a bit more cumbersome, but you can do that. And if you do that, rather than energy, you get the ecological footprint. Good. And this picture is about that. So there is a network of scientists that spend their time saying, well, how much is the ecological footprint of my computer? How much is the ecological footprint of my car? How much is the ecological footprint of airplane travel from Ghana to Trieste? And so on and so forth. And they make the computation, and the result is that you need a given amount of solar energy, or a given amount of Earth surface. And then you can compare it with the available amount. And when you do that, you realize that we are using more than we get. This is the bottom line. If on average we are using the resources of 1.5 Earth, every year the planet produces a given amount of substances, we use all of it plus 50%. So we are in over-exploitation. Another way to see it is that we use all one planet before the end of the year, let's say September or August. And then we need other resources for October, November, December. So the day in which we use all of one planet resources is the overshoot day. And as you see, in 61, we were doing fine. About the 70s, we were still bearable. Then we are going worse and worse. And of course, not all the planets not all the countries are equals, because if all of us would live as US people do, well, we will need 4 planets. While if we live as Indian people, or I'm sure Ghana people do, 1 planet would be more than enough. And this again has something to do with the social equity that we were talking before, yet you get a distribution of the planet. Italy, by the way, is not doing very well. Good. So this takes us to the definition again of sustainability. So you get this plot, maybe you see it several times. Let me see here: society, ecology, and the economy. 3 pillars for the definition of sustainability. Let's say that this is the set, the ensemble of all human activities. Not all of them are economically good. Maybe there are some subset that when you take into consideration the economical yield are profitable. So any manager would say, I'm not interested in this kind of activity. I would focus my activity, my enterprise in economic activity that are profitable here. But this is not enough if you want to be sustainable, because you have to take into consideration also society. And among all the activities, many will be socially acceptable, but others will not be socially acceptable. And you will have socially acceptable activities that are not economically profitable, and vice versa. The activity that are both socially acceptable and economically profitable are equitable. That's just name. And when you take into consideration the environment, you may get that, you may have that, you get viable activity. And those are the subset of the economically profitable activity which has a low environmental impact. And when you take into consideration the society, the environment, and the economic pillar, all of 3, you get bearable, equitable, viable, and a smaller subset of activity which are the sustainable activity. So you want to be acceptable in order to be sustainable, you want to be acceptable from an environmental perspective, a social perspective, and an economic perspective. And if you go back here, you may realize that sustainability is a concept related to time scale. There are 2 basic laws. They have been also formalized by a gay named Herman Daly, but we do not care about the name. First principle, you wanna exploit something because it's sustainable development. So you want to have an economically profitable activity, and the uptake of resources from the environment have to be slower than the rate of production of the environment. Easy. 2, the impact on the environment have to be slower than the environmental buffer capacity. Again, easy. Still easy to understand. Still, society is not going into this direction. And we need to raise our awareness about this concept. This was not meant, I didn't mean to I didn't mean to spend so much time on this introductory concept, but actually I think that is a good thing to do that. Some of you have a mathematical background, some of you have a physical background. So maybe we can spend 2 additional minutes. Do you know what is a prisoner dilemma? So this is a very game theory. When you get game theory, one of the very first thing that you see is the prisoner dilemma. And so let's say that you get 2 players. You get player A, you get player B, and the player may cooperate or they may cheat. And you get a reward, and this may be, this may be cooperate, this may be cheat, cheat, 3, 3, 1, 1, 4, 1, 4, 1. Okay? So this story goes like you may remember. You get 2 prisoners, and if they are silent, they do not betray the friend. So they cooperate, they will stay in prison for their life, but if they cooperate with the police, they said it was the other, they betrayed friends, so one of them gets a larger share and the other is punished. You may also see this like you are a farmer and you get the possibility to exploit a common ground. So you get a grass and you get a number of cows and you want to put them into the common grounds. Or maybe you can get woods from a common good. You get commons is an English word for something that is belonging to everyone. Like fish in the seas, like food in the forest, and so on and so forth. And the idea is that if you keep your fishing effort low enough at an even level, you get a share of, let's say, 3 and 3. You make the agreement, you keep it, and this is your gain. But then, during the night, one of you is greedy, and you say, well, I will increase the fishing effort. And since I will increase my fishing effort while my friend will keep the fishing effort low, my share will be larger than his. And so it will be 4 and 1. But my friend will make the same reasoning. And so he will also increase the effort. But this implies that in a very short time, the number of cows or the number of fishing vessels in the same lake is so high that the productivity of the system no longer is sustainable. And rather than get 3 plus 3 is 6, the field can give only 2. And since there is equal effort, both of you get 1 and 1. So the bottom line, you keep the effort low, you cooperate, and you get 3 and 3. Both of you increase the effort, the system became less productive and you get 1 and 1. So this is interesting because if you reason as an individual, the optimization of your own interest is to increase the effort. You can work out this by yourself when you have time. And you say, let's assume that the other player is not cooperating. What should I do? I should not cooperate because that maximizes my return. Let's assume that the other player is cooperating. What should I do? Again, I should not cooperate. If I think just to my own individual interest, the rational behavior is not cooperate, is to increase the effort. However, when you apply this not to the individual, but to the society, to the example of the individual, the optimization of the individual return does not become the optimum of the society, but became a suboptimal situation. And this has been formalized in 1964, maybe, by a man called Hardin, and it's called The Tragedy of the Commons, and point to the fact that left to themselves, individuals, even if they act rationally, do not look for the interest, do not achieve the interest of society, do not behave in a sustainable way, but they are driven towards a non-sustainable exploitation of resources. So this is to stress what? The fact that we do need to have awareness, education, training that remind us that we cannot just follow our own instinct and fish the very last fish in the ocean before someone else fish it. But we have to behave differently. But in order to do that, we need social norm and we need education, which is why, well, this is not go away. So let's move on. I waste almost almost all of the first lesson in talks. Biogeochemistry. So this is a huge range of space and time, multidisciplinary. You get molecular biologists, atmospheric scientists, geology, chemistry, biology, ecology, and you have a large use of models. And this may be steady state model and transient model. We will follow, like all the geochemists, a system approach. System means that you get a group of different components that interact. And we want to be able to understand the nature of this interaction and possibly make some. In doing so, we will rely mainly on deterministic model. As you may remember, you may have statistical model, you may have a stochastic model, you may have deterministic model, and maybe many other models. But a deterministic model means what? Means that you get a system, and the system, a piece of reality you are interested in, and you get the rest of the universe, and you say that both the system and the evolution of the system in time can be exactly defined as a function of the interaction among the system and the rest of the universe. So you will get a number of state variable, and well, here this is a bit corrupted, I'm sorry, no idea why, but it was like this. So you will get time descriptor, so this was like this. You will get that the new state at times t plus 1 of your state, so x is a vector of n components that exactly define your system, n numbers, and you will get that this is defined exactly by some function of the state variable plus some other variables, and they are the input. They are the interaction with the environment. So here, this is you, and inside here you get a number of transformations which are the relationship between your x. We will see that better in the next lessons. And as we saw before, here you get energy. Then here you get the same amount of energy. And this energy flow drive the transformation of something within the planet. So let's start from our player. We will not deal with all chemical compounds. Still, it may be worth to spend a few moments to understand where this element came from. So, you may know this better than me, the born of the universe and the Big Bang, 40 billion years ago, and you get the quarks form protons, and then you get the protons collide, and you get hydrogen, helium, and lithium. That's it. Because during the Big Bang, those are the elements that it was possible to create. Then, in order to squeeze protons closer to each other, you need energy larger than the energy available just after the Big Bang. So, all these elements from beryllium to iron had to wait for stars. When the stars were present in the universe, within the stars, you get enough heavier material, like enough lithium, enough helium. The main constituent was helium, and you say helium 2 plus helium 2, and this plus another helium 2, and this give you carbon 6. So you put together this stuff, but in order to do that, you need a lot of pressure and a lot of energy. And you do that within the stars. And in this way, you get all these elements. And then maybe carbon 6 plus again helium 2, 6, 7, 8, and you get oxygen. This way, you create all these elements. As you see, you are summing even element, so you get even element. Then, occasionally, you may have something like carbon plus 1 proton, And this give you nitrogen, odd number of protons. Here, you remember this, no? The number that you put here is the atomic weight, is the number of protons that you have in a given element. And so, if this is the distribution of element chemical compound over the universe, you see that you start from hydrogen at the very beginning, and then you get a logarithmic decay because you get this element from the previous one, so it's always smaller, 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 logarithmic decay, and you see that the even element are more abundant than the odd element, and this is the reason. So these somehow are more stable and these are less stable. So these are more abundant. Up to here, iron. These elements are even more rare, less abundant, and have been produced in later time by different processes. But basically is fusion among other lighter compounds that can take place in very specific condition. Solar system. So you get this star powder that are revolving around the star, and you get very small planets that we call planetesima, and then coil out together, and you get the real planet. And if these kinetic collisions are strong enough, everything burns, and you get magma. And in this magma, you get some smelting, so that iron go down, manganese or silicate stay up. And then when our planet cools down, you get a crust, and the crust is made by the lighter element, like magnesium, silicon, silicium, aluminium, sodium, while the heavier elements are into the middle of the planet. And then when you get this cooling down, you also get that the water vapor condense, and you get massive rain, and you get the ocean. Good. Let me check the hour. Okay, we still have some time. We are supposed to go on up to 3:30, right? Make a note. Make a note, say something, move an hand, be interactive. Okay. So you get an atmosphere, and what do you get in this atmosphere? You get elements that were heavy enough to be trapped by gravity, like oxygen, while if they were light, they just escape. So we do not have hydrogen in our atmosphere because that's too light and escape from gravity. But we have oxygen because it was heavy enough to be kept from the gravity field. And if we start from ground and we go up, we see that the pressure, which is the weight of the air above us, increase with decrease with altitude. Easy. This is the weight of the air above you. If you go up in the mountain, the layer of air is smaller, so pressure is lower. If you focus on temperature, you may expect a similar behavior, but there are some deviation. It's not like this because here you get something, the ozone, that change the profile, and here you have something else that change the profile. But I guess that you already studied this stuff, so we will not lose too much time on it. We just want to stress that the atmosphere is very thin. And let's revise very quickly how the engine works. You get the sun, and the sun is so far that we may think that the sun radiation is parallel ray. And if the incidence angle is 90 degrees, this is the surface, while here the same amount of energy, here is concentrated in a small area. So here we will be, and here is diluted over a larger area. So here we will have a high temperature, and here we will have a low temperature. Because it's a matter of density of energy. And this regional difference may give rise to atmospheric transport. Because basically what we get something like this. Here the air goes up and you get the ugly cell. Same for here. And what else? This, focus on this. Sorry. Here. You see this? So if the Earth would not be rotating, we would get something like this. So air goes up, move down, because this temperature is higher, this temperature is lower. So you get a movement like this, because you get changes in density. This go up, this go down, and you get the cell. And so basically you get this kind of movement. Then, since the Earth is rotating, rather than straight, you go straight, but the Earth rotates, and you get something like this, trade winds. Okay? But that's just because the Earth is rotating. So a combination of regional difference in solar radiation intensity and rotation give rise to these winds. And since we get tilt, this region in which you get higher temperature will be in the northern hemisphere in some moment of the year, and will be in the southern hemisphere in some other moments of the year. And so you get the season. And you get an atmospheric transport that changes with season. Now we can make some computation. We said that this is the sun, this is the radiation, this is a disk. So the solar radiation flux S, which is almost equal to this figure, but for square meter. So the radius of Earth, and so you get this surface is 4 pi r to the square. No, sorry, this is pi r to the square time S, which is the solar radiation, time 1 minus A albedo, the amount of reflected energy. So you get this energy. And then you get the same energy time alpha, a fraction of this energy, which is radiated, and this is the inflow. And then you get infrared. And Stefan Boltzmann law, you get the temperature to the 4 times the surface of Earth. And from this, you can compute the equilibrium temperature for the planet. You make the number, it's about minus 20 degrees, doesn't fit with our observation. You put a layer of atmosphere and you change the balance. So this is the atmosphere, you get like before, S, solar radiation, a fraction A, and A, of course, is a number between 0 and 1, in average 0.3 for the Earth planet. So this is a given amount of energy. Then you get Stefan Boltzmann radiation, and you can compute the equilibrium temperature for the atmospheric layer. And from this, you can also compute the Earth composition. And this is going to be better, something like this. But we will see this, I am afraid, because now the lesson is over and I was possibly too slow. So I guess that you have other lessons, right? Yes, no, do not know, maybe. Do you have other lessons after mine? Meaning, can we go on 5 or 10 minutes? Lessons. Do you have another lessons?
We don't have another lesson after this.
Good. So if you do not have another lesson, so maybe we can just use a few minutes to, I will not go deeper in this, not now, we will take it again in the next lesson, but we can revise a bit what we did, and also we can use a few minutes to decide how to share our material, meaning that I can give you the PDF of, how can I, yes, like this. I can give you a PDF of this stuff so that you get the slide that I've been using. And I can also give you, what I can give you? I can give you a chapter of a book, a PDF, that go over what I said, more or less, meaning that basically I try to give you 2 concepts. One is related to sustainability. The sustainability stuff, you cannot find it in any book, because that's just it's just a discussion. But you will get all the PDF of my presentation, and that should be enough for you to go over it and consolidate whatever you need. And this will work if you do that the sooner the better, because before you forget, and then maybe you can take your note or whatever. And then during the talk, during this lesson, we also saw something on the formation of stars, planets, elements, this kind of stuff that were the introduction to the more the more hard part of the lessons, and you will find it you can find it in many books. However, I have selected one of them, and I will give you the PDF of chapter 1 and chapter 2. Mind you, the book includes a lot of stuff, more than we covered in these 2 chapters. But again, if you go over it, you will see that something is really much deeper than what we did, and something else is what we did. That's it. In order to share the stuff with you, I needed to find a way. So either you, well, to me, the easiest thing is that you provide me with your email. If you give me your email in the chapter, or you send me your email, I can just share a folder with you, and in the folder you will get a subfolder like lesson 1 with the material of lesson 1. Does this work? So if you're okay with that, you may just put your email in the chapter. What is the chat? Here. But I do not see it. Here. Like, yeah, this is my email. Hope. And these are your email. Very good. And now, when all of you put their email, I will just get it and there. The other thing that I want to ask to you is whether or not you have any confidence with some scripting or programming, coding, whatever, like Python or Fortran or any way to run a model. That was a question. Because I think that it may be fun to actually write down short, easy pieces of code to make some, some very easy models so that you can actually play with this stuff. But in order to do that, I need to know whether or not you are familiar with some languages. So do you? Yes. So Michi said, I know. Grace said, yeah. And
Yes.
Sandra, all of you. Good. And you are familiar with, you can try it.
Python.
Python, yeah.
Fortran.
Fortran. Fortran rules. Fortran still is the choice. But I need to say it's not very friendly when you have to make lots of this kind of stuff. But that's fine. Good. So I'm just trying to copy your email. Yeah. Okay. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Go. Good. So next time maybe we will try also to see some very small coding. We will start with the temperature thing that we have just seen now. Computing the temperature of the planet. Air, and we will see how we compare. So if you have the possibility, get a computer. So that you can actually write down your own stuff. Fine?
Okay.
Good. So we see each other the day after tomorrow, same hour, right? Good. Okay. Bye.
Ciao.